Hi students, the ring activating and the ring deactivating groups. As I said that if you have a benzene ring and suppose we want to do the electrophilic aromatic substitution reaction, so electrophile can attack at any of the positions in the benzene ring because all the positions are equivalent. But now suppose we have a group, we have an ortho-para directing group. Okay, we have a ortho-para directing group. Suppose we have NH2 group. Okay, we have an NH2 group attached to benzene. Now, as we know that electrophilic aromatic substitution can occur at the ortho and the para position only, because the nitrogen has a lone pair of electron. It increases the electron density at the negative charge. At the ortho and the para positions, and therefore electrophilic substitution reaction will occur at the ortho and the para positions. And the other one is, suppose we have a group which is electron withdrawing group, which is a meta directing group. Okay, and because of its electron withdrawing effect, it will increase the positive charge at the ortho and the para positions. And now if substitution occurs over here, it will only occur at the meta positions. So we have ortho-para directing groups, okay, normally, and we have meta directing groups. One more thing in terms of reactivity, if you look at the the attack, if you look at the reactivity of the benzene towards the electrophilic substitution reaction and this molecule, the first one where you have a NH2 group attached, in the first one it will be attack will be faster than the second, than the benzene, right? Electrophilic attack on the aniline here in the first case, in this example, will be faster than the benzene, because benzene, it is a neutral molecule, right? Over here it has a negative charge, electrophile is positive charge, it is electron deficient, so its attack on the first ring obviously will be faster if we compare it with the benzene. When we compare it with benzene, the attack on the first one in the aniline is faster, right? It will be quick, okay, it will be fast, okay, and that's why we call it as a ring activating group. So we say the NH2 group is basically a ring activating group because it activates the ring to undergo the electrophilic aromatic substitution reaction. So it increases the reactivity of the ring, overall ring, right? So that's why the attack on the first ring is faster than the second one. And then if you look at the nitrobenzene, right, in the third case, in this example, in the nitrobenzene, attack will be slow if we compare it with the benzene, because we have a ring which is positively charged, right? Okay, because we got a ring which is positively charged here. Okay, this is a positively charged overall ring, so its attack on the electrophile, on the positively charged ring will be relatively, it will be slow with in comparison to the benzene. So overall order of reactivity, we can say that NH2 group is faster than benzene, and benzene attack of the electrophilic aromatic substitution reaction will be faster in benzene than the nitrobenzene, this one, correct? So we have basically, we categorize those groups again into ring activating groups as well as in ring deactivating groups, right? So ring activating group is the one which can increase the electron density at the ring, and therefore the attack of electrophile will be faster. Ring deactivating is the one which decreases the electron density at the ring, so therefore the attack will be slower. Okay, so in terms of reactivity, we can say the electrophilic aromatic substitution reaction will be faster at aniline than benzene than nitrobenzene. Okay, basically all the ortho-para directing groups, we can say that they are ring activating groups. All the meta directing groups are ring deactivating, right? This is what actually we can expect, because if you have ortho-para directing group, right, it increases the electron density, so attack will be faster. But there is one exception, right? Let me write down here the groups, certain groups which are ortho-para directing groups and meta directing groups. See, these are the ortho-para directing groups here, and this is a meta directing group. Okay, And what we find, you find the NH2 group, lone pair, there is a lone pair, there is a lone pair. All these groups, they have a lone pair. Okay, they have the lone pairs. Okay. Okay. These are the ortho-para directing groups, and they are also ring activators, right? These are the ring activating groups. Metadata directing groups, these are the ring deactivating groups, right? They increase positive charge on the ring, so therefore the attack will be slow. Only exception is this one. This is this is the exception here, right? Weakly deactivating. Alkyl groups, we will see how alkyl group can be a ring activator. Okay, but this is still a ring activator. Alkyl group is also electron donor. It is also a ring activator. Basically, every electron donor group, you can say that is a ring activator, or you can say every ortho-para directing group is a ring activator, because that will increase the negative charge, right, on the ring, so the attack will be faster. So ortho-para directing groups are also ring activators, only with the exception of the halogens. The halogens are the ring activating group. These are the ortho-para directing groups, but they are ring deactivating groups, right? They are not the ring activators. Let me explain it here. See, if you have OH or if you have OR group, whatever it is, if you attach it to the benzene ring, obviously it will increase the negative charge because it has a lone pair of electrons, and that will undergo resonance, so you get a negative charge at ortho, para, ortho. So therefore the attack of electrophile on the ring will be faster. Attack of electrophile on the ring will be faster, right? So this will be OR is actually ortho-para directing group. It's also a ring activator. This is also ring activator. Okay. Halogens, you see the halogens, if you talk about the chlorobenzene, they have lone pair of electrons there. Okay, 3 lone pair of electrons there, so they can also increase the negative charge at the ortho and the para. So therefore we can consider this chlorine as the ortho-para directing group. But the issue here is that this molecule chlorine, it has also a negative I effect. Okay, it has a plus resonance effect, due to which it can increase the negative charge at the ortho and the para positions, right? But it also has a negative inductive effect. Okay, negative I effect. So its overall effect is that it's a ring deactivating group. It withdraws the electrons through the inductive effect, it provides the electron through the resonance effect, but its negative I effect is dominant, right? Is dominant than its plus resonance effect. That's why the overall effect is that it's a ring deactivator, right? It's a ring deactivator, not a ring activator, but a moderately, or you can say the weakly ring deactivator. It's not a strong ring activator like the nitro group, like the aldehyde. It's also a ring deactivator, but a weakly ring deactivator, right? Okay, correct. So broadly we classify the ortho-para. We can say that all meta directing groups like nitro, aldehydes, they are all ring deactivators. Okay, all ortho-para directing groups, they are ring activators also. Exception is halogens only. Halogens, they are ortho-para directing groups, but ring deactivators. A weak ring deactivator, right? Okay, fine. One more thing here, how can we say the this alkyl groups are, how the alkyl groups can act as ortho-para directing groups? How is this possible, right? How can we say that this methyl group is a ortho-para directing group, right? Okay, with these examples it's clear that they have lone pair of electrons, but how can the alkyl groups be? Suppose if you attach a methyl group, attach it to the benzene, it does not have a lone pair of electron, so we cannot consider the methyl group as a ortho-para directing group. But it has alpha hydrogen atoms here, right? You can see that it has alpha hydrogen atom, and alpha hydrogen atom when taken, with a double bond, okay, so you have alpha carbon with alpha hydrogen atom. So this alpha, it has 3 alpha hydrogen atoms here, 1, 2, 3. They can undergo the hyperconjugation, right? Through hyperconjugation, we know that this electron pair will shift here, it will go here, so it will increase the negative charge at the ortho position, okay. So if you draw a structure, that will be like this. If you draw a hyperconjugation structure, it will be like this. H plus is here, and you got a double bond with a benzene ring, negative charge here, and then this negative charge will overall, it will delocalize over here, then it will go back down, so you get a negative charge at the ortho and the para positions in other canonical structures, okay. So therefore we can say the methyl group is also ortho-para directing group. So therefore the electrophile will attack at the ortho and the para positions, okay. But the effect, the effect is through hyperconjugation, right? This is not a very strong effect, right? This is not a very strong mechanism of electron displacement, right, like the resonance effect has. So if you compare this methyl group with the NH2 group, the NH2 group is a much stronger ring activator because it releases the electron through the resonance effect, and the resonance effect is dominant than the hyperconjugation effect, correct? It provides electrons. So NH2 is also ring activator, it's also an ortho-para directing group, but the thing is that NH2 is also ortho-para directing group because it increases the negative charge at the ortho and the para position. Methyl group also increases the negative charge at the ortho and the para position, but there's a difference. The difference is that NH2 group, it provides electrons through the resonance effect, that's why it's a very strong ring activator. Methyl group, it provides electrons through the hyperconjugation, so it's a weakly activating group. It's not a strong activating. There's a difference, right, among the ortho-para directing groups also, or among the ring activators also there is some difference, right? Okay, so let's discuss one more example here, okay. So NH2 group is a strong ring deactivator. Ring activators, we can classify them either into strong ring activators, moderately ring activating, and the weakly ring activating groups, right? Okay, fine. So over here, if you look at the, we have discussed aniline, that is clear, but let's have a comparison of aniline with other groups. Suppose if you have aniline, and let's compare it with the, suppose if you have a group like this, if you have NH, it has NH, then a lone pair here, benzene ring, let's say there is a C double bond O, CH3 attached to it. In both cases we have a nitrogen which can undergo resonance. It will increase the negative charge at the ortho and the para positions, right? So it will be like this. Let's have a comparison here, right? If in this case also electron pair, okay, goes here, it goes over here, right? So what you get? N C double bond O, CH3 here, H, positive charge, and then you get a double bond here, negative charge, go to ortho position, and then the same negative charge will go to the para and the ortho as in this case. So we can expect it to be having the same method, right, of electron donation. So the two groups should be having the same activity, right? Okay, in terms of ring activating effect, they should have the same, but we find that this group is actually a moderately activating, while as NH2 is a stronger one, right? It's a much stronger than the NH C double bond O CH3 group. The reason because this lone pair of electron over here in this molecule, it can undergo the resonance. It has two options, right? Actually, it's actually it's possible. One possibility is this one that we have written here. Another possibility, the electron pair can shift in this direction. Okay, so it can have a residue structure over here also, right? So you can get a group like this, NH, then a double bond, CO negative there, CH3, and then the benzene ring. Now the electron pair on the NH2 group, it can follow the second path, right? Okay, that means this NH2 group, it can either be under resonance with the benzene ring or it can be under resonance with the carbonyl group. So therefore, once you attach a carbonyl group to it, basically it will undergo resonance over, more dominantly with this one, with the CO, because that's the electron withdrawing group. Okay, CO is electron withdrawing group. It has more electronegative atoms, so it has two options actually to undergo the resonance. So therefore, its effect will be slightly lesser, right? Okay, NH2 group, the electron pair, the lone pair of electrons with the nitrogen, it has now a benzene ring attached to one from one side, from another side it has a CO group. So therefore its effect on the NH2 group is a little bit lesser as compared to here. There's only one possibility for this electron pair to undergo resonance, that is only the benzene. But over here we have two options, right? It can either resonate with the CO group or with this one. Got it or not? I think it should be very much clear now, right? It should be very much clear. But halogens are ring deactivating groups, right? Okay, these are the ring deactivating groups. These are again the same examples here. Now let's take some couple of questions on it, right? In terms of the reactivity, suppose if you do any if you do a chlorination, right? Okay, the question is the chlorination of the following molecules, right? What will be the ring, what will be the order of reactivity? Okay, what will be the order of reactivity? Suppose if I take the benzene ring first, a simple benzene, this is the one, and the second one is the nitrobenzene. Okay, a nitrobenzene, this is the second molecule, and the third one is actually the phenol, OH. Okay, the electrophilic aromatic substitution reaction, any electrophilic aromatic substitution reaction will be faster with the phenol, with the third one, because it's the ortho-para directing group and it's a ring activator, right? Okay, so we can say OH is a ring activator. Okay, this is the ring deactivator, and obviously the attack on the electrophilic substitution or attack on the ring will be faster for the third one, right? Then it will be the first one, the benzene, and then the last one, this one, right? Because ring activating groups, the attack is faster than benzene, and ring deactivating groups, the attack is slower than even the simple benzene. Among the groups, let's take one example here. Suppose we have NH2 group. Okay, we have, for example, a chlorobenzene, we have a simple benzene with, okay, let's take NO2 group, and then we have a CH3 group, and then say we have a simple benzene. The electrophilic aromatic substitution reaction, right? First one, this is the second one, third one. What will be the order of reactivity, right? What will be the order of the reactivity? I think the first one will be the fastest one, right? The first one, because that's the ring activator, isn't it? This is the ring activator. It's ortho-para directing group, but it's also ring activators. We know that all ortho-para directing groups are ring activators except halogen, which is a weakly ring deactivating group. Okay, so chlorine, it's ortho-para directing group. It has a lone pair of electrons, but the problem is that it is ring deactivator. Okay, that's the exceptional case. Halogens, they are the exceptions. Nitro group, this is also ring deactivator. Methyl group, it's a ring activator actually, right? Now ring activators, the attack is faster, right? But among the two ring activators, NH2 group is a strong ring activator than the methyl group. So attack will be first faster on the first one, and then it will be the fourth one, because always ring activators are, they undergo faster ES reactions, right? Then the simple benzene, which is the fifth one, right? Now we have two ring deactivators here, chlorobenzene, nitrobenzene. Okay, how do you differentiate? Both are ring deactivators actually. This is a strong ring deactivator. Its effect is much stronger than the chlorine, right? The chlorine also deactivates the ring, but not so strong, right? It's a weakly ring deactivating group. We know that it's a weakly ring deactivating group. But nitro group is a very strong ring deactivator. Its effect is very much. It will deactivate the ring to a very high extent. Okay, chlorine also will decrease the reactivity, but to a smaller extent relatively. So therefore the second one will be the faster one, right? And then the third one. Now this is the order of reactivity towards any electrophilic substitution reaction for these molecules. Okay, fine. So I hope you got this concept. Okay, so thanks for watching the video. See you in the next lesson. Bye for now.